All right, hello there, and welcome back to another video. Today we are going to go over section 4.8, which is on L'Hopital's rule. And we're just going to go quickly and do the problems in this section. We'll read the learning objectives though. Our learning objective 4.8.1 is to recognize when to apply L'Hopital's rule. 4.82, identify indeterminate forms produced by quotients, products, subtractions, and powers, and apply L'Hopital's rule in each case. Okay. And then finally, describe the relative growth rates of functions. Okay, so we'll read this introductory paragraph just to get us started, and then we'll jump into the problems. It says, in this section, we examine a powerful tool for evaluating limits. This tool, known as L'Hopital's rule, uses derivatives to calculate limits. With this rule, we will be able to evaluate many limits we have not yet been able to determine. Instead of relying on numerical evidence to conjecture that a limit exists, we will be able to show definitively that a limit exists and to determine its exact value. Okay, so let's go ahead and take a look at L'Hopital's rule. Let's see, I'm sure they have the theorem in here somewhere. It looks like they have a proof of the of the theorem maybe in here somewhere. Yep. Um, but essentially, this is what the theorem is. So suppose f and g are differentiable functions on an open interval containing a, okay, except possibly at a. If, so here's the important part, the limit as x approaches a of f of x is 0, the limit as x approaches a of g of x is 0, then, and I'll write this other part out, what's the limit as x approaches a of f of x over g of x? Well, it seems like it should be 0 over 0, and that's the form that we end up getting when we do direct substitution. But L'Hopital's rule, this mathematician, proved that this is equal to the limit as x approaches a of the derivative of f divided by the derivative of g. Okay. And derivatives a lot of times are simpler than the original function. So this can help us to simplify a limit problem. Okay, and says, assuming the limit on the right exists or is positive or negative infinity. This result also holds if we are considering one-sided limits or if a equals infinity or negative infinity. Um, okay, nice. So they provide a proof for the theorem. We won't go over that. Um, yeah, and so just one quick note. Let's do it, and then we'll talk about this note that's here. Note that L'Hopital's rule states we can calculate the limit of a quotient f over g by considering the limit of the quotient of the derivatives f prime divided by g prime. So let's take a look at an example. And we'll just do the ones here. So we are looking at the limit as x approaches 0 of 1 minus cosine x divided by x. If we do direct substitution, we could get 1 minus cosine of 0 divided by 0. And cosine of 0 we know is 1. So we get 0 over 0. This 0 over 0 is what is called an indeterminate form. Indeterminate form. Okay, so when we get this 0 over 0 behavior, L'Hopital's rule says, well, actually, this limit as x approaches 0 of 1 minus cosine x over x is equal to the limit as x approaches 0 of the derivative of 1 minus cosine x. That would be sine x, right? The 1 has a derivative of 0. Cosine has a derivative of negative sine, but since there's a negative in front of it, those double negatives cancel each other out and we get sine x. And then the denominator, the derivative of x, is 1. And so now using direct substitution, this is now a different limit equivalent to the original. We would get sine of 0 over 1, which is 0 over 1, which is 0. The answer is 0. And so we want to be careful, for a couple reasons. The first thing is notice that I took the derivative of cosine x, 1 minus cosine x, and got this sine x. And then I took the derivative of x and got the derivative 1. We want to be careful not to look at that fraction and think that we have to use the quotient rule. It does say that up here in this note. It says it is important to realize that we are not calculating the derivative of the quotient f over g. We're doing the derivative of just f to get f prime, and then the derivative of g to get g prime. And that's how L'Hopital's rule works. We find the derivative of the numerator by itself and find the derivative of the denominator. Um, this is not kind of clashing with what we said before. The derivative of f over g would require the quotient rule, but we're not finding the derivative of the quotient. We're finding the derivative of each of the individual functions in the numerator and denominator separately. Okay, good. Now, because of this, we also want to be careful not to say, oh, look, hey, 0 over 0 ended up being equal to 0 here. So it's always going to be 0. That's not true. Um, Usually, 0, oh yeah, 0 divided by a non-zero number like 2, that's equal to 0. Whereas something divided by 0 is undefined. Right? And so that's why this is an indeterminate form, because is this equal to 0 or is this undefined? Because we always say 0 divided by anything is 0. But more accurately, that should be said as 0 divided by any non-zero number is equal to 0. And then any non-zero number divided by 0 is undefined. But so what happens when you divide 0 by 0? Well, that's where you end up with an indeterminate form that you need to use L'Hopital's rule to determine. Sometimes the answer could be 0, sometimes it could be undefined or does not exist, and sometimes it could come out to be something like 7. So the indeterminate form needs L'Hopital's rule to help us determine what the limit is. Okay, so let's take a look at another example. Um, Here we'll look at the limit as x approaches 1. And so I'm going to put ds here for direct substitution. Let's just try to plug in 1. Pi times 1 divided by the natural log of 1. The sine of pi is 0. The natural log of 1 is 0. And so this is an indeterminate form. And let me see here. Let me make sure I'm writing this correctly. Is it indeterminate or indeterminate? It's N-A-T-E. Okay, sure. So indeterminate. Oh, and that's what I wrote this time. Okay. Nice. Okay, so L'Hopital's rule then. L'Hopital's rule says that the limit as x approaches 1 of sine of pi x divided by the natural log of x is equal to the limit as x approaches 1 of the derivative of sine of pi x is cosine of pi x. Using the chain rule, we have to multiply by pi divided by the sine of the derivative of natural log of x is 1 over x. And now I can try direct substitution again, which gives me the cosine of pi times pi divided by 1 over 1. And that's going to be equal to, let's see, what's the cosine of pi? Pi over 2. Cosine of pi is -1. So this is equal to -1 times pi divided by 1, or just negative pi. So notice here's a good thing that we should see here, that the indeterminate form of 0 over 0, in this case, got us negative pi, right? That the limit ended up being negative pi. So don't just think just because you see 0 divided by 0 that the answer is going to be 0 or undefined. It's possible it comes out to something else. Okay, so notice, yeah, we can check our answers here. 0 for the first one, yes, and negative pi for the second one. Nice. Let's take a look at another example. Um, yeah, why not this one here? So again, I'll do direct substitution. We really do need to directly substitute to determine whether L'Hopital's rule can even be applied. Because notice that if we go back to the way that the theorem is stated, we have to have that the limit of the top function is 0 and the limit of the bottom function is 0. Okay, and that's for what's called the 0 over 0 case. So we first have to verify that through direct substitution. If that is the case, 0 over 0, then we can use L'Hopital's rule to take the derivative of the top and the bottom, and then take the limit of that new quotient. Okay, so direct substitution. Oh, and this is the limit as x approaches infinity. So when we plug in infinity, what we're looking at is the behavior of the function as x approaches infinity. So we know that 1 over x will approach 0 as x approaches infinity. So this is going to be e to the 0 minus 1 over 1 over infinity is going to be approaching 0. And so this is 1 minus 1 over 0 or 0 over 0. So we have checked that we are getting the indeterminate form. Um, and officially what we're doing here is we are looking at the limit as x approaches infinity of the top, e to the 1 over x minus 1. And we saw something called the composite function theorem before that said we can push this limit into the inner function of a composition of functions. And so this becomes e to the limit as x approaches infinity of 1 over x minus 1. The limit as x approaches infinity of 1 over x is 0. And that's where we're getting 1 minus 1, which is giving us 0 on top. Okay, so we should check that we're getting 0 on top and bottom. Once we do that, we can then say, because of L'Hopital's rule, L'Hopital gives us that the limit as x approaches infinity. So this limit stays the same. Let me write the original limit here. But just to say that this is equal to now this new limit, the limit as x approaches infinity of the derivative of the top. So what's the derivative of e to the 1 over x? Well, that's e to the 1 over x times the derivative of the inner function. The inner function is 1 over x, which is x. So 1 over x is x to the negative 1. Its derivative is negative 1 x to the negative 2, which is negative 1 over x squared. Okay, so negative 1 over x squared. Because of the chain rule, the derivative of the minus 1 is just 0. And the bottom is 1 over x, so its derivative is going to be negative 1 over x squared. And notice, hey, this cancels very nicely. So now we have e to the 1 over x. We're taking the limit as x approaches infinity according to the, so let me write it, the limit as x approaches infinity of e to the 1 over x. And so really here we're looking at the behavior as x goes to infinity. If x goes to infinity, this exponent is going to go to 0. So that the answer is going to be e to the 0, which is 1. Okay. Yeah, so e to the 0, which is equal to 1. And there we used again this idea, the composite function theorem, from a previous section. Excuse me. Okay, nice. Now let's take a look at our last one. Again, direct substitution. We plug in 0 in this case. So the sine of 0 minus 0 over 0 squared. That's 0 over 0. So L'Hopital's rule can be applied. So L'Hopital's rule says the original limit is equal to the limit as x approaches infinity. Sorry, as x approaches, it should be the same thing here. So x approaches 0. Notice we did have one that where the limit as x approaches infinity, uh, that just stayed infinity here. That's what that note was at the end here. It says that notice that a could be infinity or negative infinity. Um, yeah, it doesn't need to be finite. Okay, but in this case, it is finite 0. So this is going to be equal to the derivative on the top. Sine x, the derivative of that is cosine x. Minus x has a derivative of -1, and x squared has a derivative of 2x. And so now we can do direct substitution. And so we get, uh, after direct substitution, we get, now I'm going to write it up top here because I'm running out of room. But if you do direct substitution, you're going to get cosine of 0 minus 1 on the top and 2 times 0 on the bottom. Cosine of 0 is 1, and 1 minus 1 is going to give you 0 on top, and we get 0 on the bottom. So notice we have to apply L'Hopital's rule again, right? We got another indeterminate form. Since I'm running out of room here, I won't show that, but we would, show that like I did in red. And then we can say, okay, well, L'Hopital's rule applied again tells us, okay, the limit as x approaches 0 of the derivative of this numerator. The derivative of cosine x is negative sine x. The derivative of -1 is 0. And the derivative of 2x is 2. So now we can try direct substitution. Again, negative sine of 0 over 2. This is 0 over 2, which is 0. All right, so the answers seem to be, let's see here. It came out, the answers were 0, negative pi, 1, and 0. Okay, yeah, so the answer could be anything really when you get an indeterminate form. Um, the answer could have been 7 for one of these if the numbers were right. So don't just, see 0 over 0 and think, okay, well, that must be equal to 0 or must be undefined. No, it really depends. So you need to do the derivatives. Okay, just verifying our answers. We got 0 here and, sorry, 1 there and 0 here. Okay, so here's a problem you can try on your own. Do try that one. Now we can see these answers. Maybe I can show this actually. Um, let's do it here with this one, with part D. How can we tell what the answer is going to be? Well, we can graph the function and see the behavior of the y values as x approaches, a, which, let's see, for part D, that would be 0. So sine x minus x over x squared. Sine x over x squared, and then there was a minus x. Okay, here we go. We can kind of stretch this out. As x approaches 0, yeah, pretty clearly there, the function is approaching 0. The y value is approaching 0. You can see it right in that first, as x approaches 0, y approaches 0 from both sides. So it looks like the answer is 0. Some of them could be a little bit more complicated. Yeah, maybe the sine of pi x over the natural log of x. Let me look at that one as well. Sine of pi x divided by the natural log of x. Okay. Okay. Well, actually, yeah, so it has some weird behavior to the right, which makes sense because it's a sine function. But okay, that one's pretty clear also from the graph. As x approaches 0, y approaches 0. So was that one also 0? Oh wait. We're looking at the limit as x approaches 1 though. So okay, oops. So let's go to 1. What's the y value approaching? Something a little bit less than 3. If we graph x equals 1, where x is equal to 1, and see where these two intersect. Oops, it doesn't show me the point of intersection. But you can see it's approximately 1. See, yeah, the function is undefined when x equals 1 because the natural log of 1 in the denominator is equal to 0. So it is undefined, um, but it's approximately negative 3.14. Um, so it's negative pi. Nice. Okay. Okay, nice. So that's not too bad. That's L'Hopital's rule. So is 0 over 0 the only indeterminate form? The answer is no. There are other indeterminate forms that we can use L'Hopital's rule for. And here is the other case, the infinity over infinity case. So let's see what it says. We can use L'Hopital's rule to evaluate limits of quotients f of x over g of x, in which f of x approaches positive or negative infinity, and g of x also approaches positive or negative infinity. Limits of this form are classified as indeterminate forms of type infinity over infinity. Again, note that we are actually not actually dividing infinity by infinity. Since infinity is not a real number, that is impossible. Rather, infinity over infinity, okay, is used to represent a quotient of limits, each of which is positive or negative infinity. Okay, so let's take a look at the theorem. Suppose f and g are differentiable functions over an open interval containing a, except possibly at a. Suppose, okay, so here's the important part. The limit as x approaches a of f of x is infinity or negative infinity, and that the limit of the denominator function, g of x, is equal to infinity or negative infinity. Then the limit as x approaches a of f of x over g of x, which is going to look like infinity over infinity, is equal to, this theorem shows the equality of this original limit with the limit as x approaches a of the derivative of f divided by the derivative of g. Assuming the limit on the right exists or is positive or negative infinity. This result also holds if the limit is infinite, if a equals positive infinity or negative infinity, or the limit is one-sided. Okay, nice. So let's take a look at a couple of these problems. And so we want to look at the limit as x approaches infinity of 3x plus 5 over 2x plus 1. And so one thing that we should note here is that the limit, well, this is what we need to show of 3x plus 5. This is positive infinity. The limit on top is positive infinity. The numerator is growing infinitely large. The denominator of 2x plus 1, as x goes to infinity, this is also going to positive infinity. And so we have an infinitely large, or a numerator that's growing infinitely large and a denominator that's growing infinitely large. So what's the limit going to be of this quotient here? What value is going to be approached by this function? Well, L'Hopital's rule, I'll abbreviate just LH, says that this limit is equal to the limit as x approaches infinity of the derivative of the top. The derivative of the top is 3. The derivative of the bottom is 2 of 3 over 2. And this does not depend on x. That's just a constant. So the answer is 3 over 2. So, wow, that's pretty cool. Something that, is growing infinitely large divided by something else that's growing infinitely large, the ratio ends up just working out to be a constant of 3/2. And you can kind of see why there, because they're both degree 1 polynomials, and one of them grows to the size of 3 times x, the other one is 2 times what x is, and the ratio is 3 over 2. Okay, yeah, good. So now that one you could actually even say, hey, I could have solved that in pre-calculus. When I took pre-calculus, they told me that when the degree of the numerator and the degree of the denominator are equal, then the horizontal asymptote is just going to be y equals the leading coefficient on top divided by the leading coefficient on the bottom, so 3 over 2. And yep, that's true. But part B was not probably covered in pre-calculus. This is another problem where we can apply, it looks like we're going to be able to apply L'Hopital's rule. So let's go ahead and verify first that we could apply L'Hopital's rule. Let's take a look at the limit. Um, so here we're doing direct substitution in a sense. Um, but when we say direct substitution, what we're doing is we're essentially taking the limit as x approaches 0 from the right of the natural log of x, and the limit as x approaches 0 from the right of cotangent x. And this is going to be equal to, let's see, on top we get, we know the behavior of natural log of x is that it goes down to negative infinity. And the cotangent of x, what does that do? Um, Cotangent of x, let's graph the function. Hopefully we remember the graph from pre-calculus. Tangent looks like this, and cotangent looks, if my memory is correct, looks like this. And so the limit as x approaches 0 from the right is going to be positive infinity. So since we have an infinity divided by another infinity, it doesn't matter if they're positive or negative. L'Hopital's rule here will apply. And so the original limit, let's say here, just so I don't have to, oh, I'll rewrite it. Why not? Let's not be lazy. The limit as x approaches 0 from the right of natural log of x divided by cotangent x is equal to the limit as x approaches 0 from the right of the derivative of natural log of x, which is 1 over x, divided by the derivative of cotangent x. The derivative of cotangent x is negative cosecant squared x. Okay, and now we look at the limit as x approaches 0 from the right. And 1 over x is also going to have an infinite limit. 1 over x looks like this. And the limit from the right is positive infinity. Okay, so cosecant of x squared. The cosecant function, well, we remember that cosecant x is equal to 1 over the sine of x. And since sine of x starts at 0, has a y value of 0 when x equals 0, then the cosecant x is going to look, it's going to be undefined at x equals 0, since it's the reciprocal of 0. And we'll have cosecant of x is going to have vertical asymptotes at 0 and at pi, and then it's going to do something like this. Okay, so the limit there is also positive infinity. Okay. So it looks like we can use L'Hopital's rule again. Okay, well, that's fun. Um, and actually, you know what? Since we have uh infinity, let's see, give me 1 second here. Okay. Yeah, infinity over infinity. Um, yeah, there's a couple of ways to approach this. Um, yeah, recognizing that 1 over x can be written as, we can essentially just move this x to the denominator, and the cosecant function is 1 over sine. We can move, just write this as, let's go ahead and rewrite this as the limit as x approaches 0 on the right of negative sine squared x over x. Right? You do a little bit of algebra and you can get that. And so the limit here is still going to be, you can do direct substitution and see that you're going to get 0 over 0 just by plugging in 0. So Um, let's go ahead and apply L'Hopital's rule again. Take the derivative of both the top and the bottom, and we get the limit as x approaches 0 from the right of, here, what's the derivative? This is going to be negative 2 sine x times the derivative of the derivative of the inner function sine, which is cosine, and then divided by 1. Okay, that's really nice. The denominator is just 1 now. So now with direct substitution, we can see that we're going to get negative 2 times the sine of 0, cosine of 0. The sine of 0 is 0, so this whole thing is going to be 0. All right, so that original limit is equal to 0. Cool. All right, very good. And we can read the words there if you want. All right, so you try this problem here on your own, see if you can get an answer. And you can answer it just by, once you get your answer, you can check it by graphing it on Desmos.com. All right. As mentioned, L'Hopital's rule is an extremely useful tool for evaluating limits. It is important to remember, however, that to apply L'Hopital's rule to a quotient f over g, it is essential that the limit of f of x over g of x be of the form 0 over 0 or infinity over infinity. Consider the following example. Okay, so let's go take a look at this problem here. Now it says consider the limit as x approaches 1 of this function. Show that the limit cannot be evaluated by applying L'Hopital's rule. So sometimes students will see a limit like this, the limit as x approaches 1 of x squared plus 5 over 3x plus 4, and just say, okay, I'm going to use L'Hopital's rule. I'm just going to take the derivative of the top and the derivative of the bottom. So that's 2x divided by 3. And if I do direct substitution now, I get 2 times 1 over 3, or 2/3. But this is not correct. The mistake is here in assuming that you could apply L'Hopital's rule, because we should check first by plugging in by doing direct substitution. Direct substitution shows us that after plugging in 1, we get 1 squared plus 5 divided by 3 times 1 plus 4, which is 6 over 7. And so that's the answer. We were able to do direct substitution and just solve the problem just by using substitution. Notice that that's different than 2/3, because direct substitution, L'Hopital's rule gave us the wrong answer because L'Hopital's rule didn't apply here. Okay, so it says here, because the limits of both the numerator and denominator are not both 0 or not both infinite, we cannot apply L'Hopital's rule. Okay, you can see that it would give you the wrong answer. All right, so be careful there. All right, let's study a little bit more about other indeterminate forms, even though these will not be a major part of our class. But just very quickly, we'll take a look at one of these problems. So other expressions that could end up using L'Hopital's rule are of the type 0 times infinity. So, they're kind of strange expressions because you say, what's 0 times infinity? 0 is a very small, or it's a 0 times anything is 0. But if that other thing that you're multiplying 0 by is getting infinitely large, it can cause problems because here, when we're talking about 0, when we're talking about 0, 0 times infinity, we're saying as something approaches 0, multiplies something that's approaching infinity, what is that product approaching? Well, it depends how fast the one object is approaching 0 and the other is approaching infinity, right? The speed at which they approach these values is relevant here. Infinity minus infinity, again, also, well, it depends which one of these is approaching infinity faster. So infinity minus infinity won't always produce an answer of 0 if the first infinity is something that's growing infinitely large faster than the one being subtracted. 1 raised to the infinity, infinity to the 0, and 0 to the 0. These are also considered indeterminate forms. Now, these are not going to be forms where we can apply L'Hopital's rule right away. We need to do some sort of algebraic manipulation to convert them to to these 0 over 0 or infinity over infinity forms. So then we can apply L'Hopital's rule. Okay, that's exactly what that says there. So let's take a look at one of these problems here. Yeah, we'll take a look at this one here. X times the natural log of x. So if we do direct substitution, um, then so direct substitution, we're going to get 0 times, and the natural log of x, as x approaches 0, this is negative infinity. So 0 times infinity, what is that equal to? Is that 0? Is that infinity? Is that something else? Well, this should be, ringing a bell here and say, hey, that I learned in the section for L'Hopital's rule, and so maybe I can manipulate this somehow to be able to apply L'Hopital's rule to answer this question. And so here's where it is, the limit as x approaches 0 plus. So how do we do this? It's going to take a little bit of an algebraic trick um, of x times the natural log of x. The way that we can figure this out is by thinking of x as x over 1, a fraction, and remembering the rules for dividing by fractions. We could write this as the natural log of x divided by 1 over x. Because if you divide by 1 over x, that's the same thing as multiplying by the reciprocal of 1 over x, which is x, and that would get you x natural log of x. So you're kind of like unsimplifying this expression. And we do that because now the limit as x approaches 0 of the natural log of x, that's going to be negative infinity. And the limit as x approaches 0 of 1 over x, 0 from the right, that's going to be positive infinity, right? We know what 1 over x looks like. We already went over that earlier. As we go to 0 from the right, this goes to positive infinity. And so we have infinity over infinity situation, which allows us to use L'Hopital's rule. So we had to manipulate this expression to be able to evaluate the limit. Okay, so now let's use L'Hopital's rule. Uh, after L'Hopital's rule, so remember that this is an indeterminate form. So L'Hopital's rule says we can take the derivative of the top. So let me write my limit first. The derivative of the top is 1 over x. The derivative of 1 over x, we did that one earlier, is negative 1 over x squared. And so now that we've taken our derivatives, we've already got the indeterminate form of infinity over infinity, and we've taken our derivatives. We can now try to simplify this. So we know a fraction divided by a fraction is just the first fraction times the reciprocal of the second. And so this is equal to the limit as x approaches 0 from the right of, let's see, one of these x's will cancel with one of these x's, and so we get negative x. And here we can now do direct substitution. There isn't even a fraction anymore to worry about, so this is going to be the opposite of 0 or just 0. Nice. So again, I want to mention that 0 times infinity doesn't always end up coming out to be 0, so we do have to be careful. Don't just assume because this one came out to 0, they all have to come out to 0. No, that's not true. All right, oh, and there's the graph. Nice. Okay. All right. Another indeterminate form would be infinity minus infinity. And here, maybe we'll just read it very quickly. Here we can look at this problem and see that uh, as x approaches 0 from the right, let's see. Hmm. As x approaches 0 from the right, 1 over x squared, we know what that looks like. That looks like this. So that would be positive infinity for the limit of the first function, 1 over x squared. And then I don't know what 1 over tangent x, that's just cotangent x. And we saw that one earlier. There was a vertical asymptote, and the graph looks something like this. So that function also goes to positive infinity. And so we have infinity minus infinity here. And so the way to evaluate this kind of limit is to just try to combine the fractions. And then, what does that involve? Getting a common denominator, in this case, x squared tangent x. And once you combine the fractions into one, um, let's see, what did they do here? We can apply L'Hopital's rule, taking the derivatives of the numerator and denominator. Ah, yeah, so at this step here, once they combined the fractions, they went from infinity minus infinity to a single fraction, and we can see that the numerator goes to 0, the denominator goes to 0 as well, and so we have the 0 over 0 situation. So now L'Hopital's rule can be applied. They do the derivatives. There's the derivative of the top, the derivative of the bottom function, and they show that the numerator goes to 1, the denominator goes to 0, and so that fraction will get infinitely large, and so the answer is positive infinity. All right, so there's another problem there for you to try. And then the last one here that we'll look at for L'Hopital's rule is uh, one of the type 0 raised to the 0 or infinity raised to the 0. With these with these ones that have an exponent of 0, or even 1 to infinity, we're going to need logarithms because we know that a log has a property where it can bring down, excuse me, uh, the exponent. And so they kind of outline that here. Let's go ahead and take a look at one of these problems. So um, let's see if we can find a good one. Is this going to be good? 0, 0 to 0. Oof. Wow, that is ugly. Okay. Mm, yeah, maybe let's go ahead and take a look at we'll take a look at the simpler one here, just to kind of get us into get us the idea of this. We won't focus on this too much, um, but it is good to see once. So, let's take a look at the limit as x approaches infinity of x to the 1 over x. And so let's take a look at the behavior here as x goes to infinity, so we can call this a direct substitution. The base is going to grow to infinity because it's just x and x is going to infinity. And then 1 over x, we know that 1 over x goes to 0 as x goes to infinity. So we have that behavior of infinity to the 0. This should tell us, okay, I remember that form from L'Hopital's rule. So what can I do here? Well, uh, here's what we can do. X to the 1 over x. We can apply the natural log function. So we say let y equal this limit here as x approaches infinity of x to the 1 over x, and apply the natural log to both of these sides of the equation. And then we can apply the natural log to the function. So we have I'm going to leave the natural log of y alone here, but just remember, we'll bring it back in a little while. We're pushing this continuous function past the limit. So the natural log of x to the 1 over x. We remember that rule from pre-calculus that allows us to bring down our exponent. And so this is equal to the limit as x approaches infinity of 1 over x times the natural log of x. Or let me write it even better here as the natural log of x over x. And notice, what do we have now? The natural log of x over x. And both of these are going to go to infinity as x goes to infinity. So now we have an indeterminate form that we can apply L'Hopital's rule to. So L'Hopital's rule says that we can take the limit as x approaches infinity of the derivative of natural log of x, which is 1 over x, and the derivative of x, which is 1. Okay, this is nice because this is just the limit as x approaches infinity of 1 over x, which we know is 0. So now, is 0 our answer? The answer is no, because remember a moment ago that we said, before we took the natural log, we said we set y equal to our limit. And so we want to find the value of y. But right now we have that the natural log of y is equal to 0. So we set the natural log of y equal to 0. The way that we solve this limit here, or sorry, this equation is by exponentiating both sides. So y is equal to e to the 0, which is equal to 1. So the limit, y equals the limit as x approaches infinity of x to the 1 over x. This is equal to 1. Nice. Okay, very good. Let's go ahead and move on. Again, I just want to mention it one more time, but this limit of infinity to the 0, um, maybe you could say, well, hey, I remember anything to the 0 is equal to 1, and this answer came out to 1. But the infinity to the 0 is not always going to come out to be 1. So you really do need to do the problem. Here, let's see, what do we get? We have infinity and then to the 0, right? If we do direct substitution. So let me graph this really quick just so we can see what this does as x approaches infinity. X to the 1 over natural log of x. Okay, there's our... And so what does this do as x approaches infinity? It looks like it's approaching a value of, looks like e, 2.7 approximately, right, as we go very far out. Okay, so, okay, so there you go. The answer is not always 1. In this case, it ended up coming out to e, which, hey, there was an e involved in our little solution there, but our e was raised to the 0 for that problem. And so um, e to the 0 is 1, but it looks like this one works out to e somehow. Okay, so you can try that one on your own. I'll skip this one here. It's very similar. It's just, it looks like it's going to apply L'Hopital's rule a couple times, so it's a little bit longer. All right. The last thing that we can say here is that limits can also be used to determine relative growth rates of functions. And so we'll show this very quickly here. It says, example 4.45, comparing the growth rates of natural log of x, x squared, and e to the x. For each of the following pairs of functions, use L'Hopital's rule to evaluate the limit as x approaches infinity of f of x over g of x. Okay, so sure, let's try to do that. The limit as x approaches infinity, we'll do part A, of f of x, which is x squared, over g of x, which is e to the x. So we can see after direct substitution that x squared is going to go to infinity, e to the x is going to go to infinity. So infinity over infinity allows us to apply L'Hopital's rule. Since we're at the end of our, close to the end of our video, at the end of our time here, I'm kind of skipping a little bit, but um, we do the limit as x approaches infinity of the derivative of the top over the derivative of the bottom. The derivative of x squared is 2x. The derivative of e to the x is e to the x. So again, if we do direct substitution, we get infinity on top. 2x goes to infinity as x goes to infinity, and e to the x goes to infinity as well. So again, we can apply L'Hopital's rule. The limit as x approaches infinity of 2 over e to the x. Now we have the top is approaching 2 because it's constant, and the bottom approaches infinity. And so we know that when a denominator gets infinitely large and the numerator is constant, this is going to approach 0. And so so basically what we're saying is the bottom function is growing much faster than the top function. And so since we got 0 here, that means that the growth rate of the bottom function is a lot faster than the growth rate of the top function. And this is something you might already know. A polynomial like x squared does not grow as quickly as an exponential function like e to the x. So that's why exponential growth is something that's talked about commonly. If something grows exponentially, it's growing really fast. Okay, and so we can see this statement here that, let's see, we say G grows more rapidly than F as X approaches infinity if the limit of F over G is equal to 0. And if you were to take the reciprocal, put G on top and F on the bottom, then the top function would grow faster to infinity. And so that limit would be not 0, but infinity. Okay, so we did the one in the box here. We showed that the bottom function grows faster. The quotient went to 0. So e to the x grows a lot faster. And the last one here, f of x, the limit as x approaches infinity of f of x over g of x. Let's see here. The top goes to infinity, the bottom goes to infinity. So if we apply L'Hopital's rule, then we get the limit as x approaches infinity of 1 over x divided by the derivative of the bottom, which is 2x. And so this is equal to, let's see, we can actually simplify this using algebra. 1 over x divided by 2x over 1. We can flip and multiply, and we get 1 over 2x squared. And here it's not too hard to see that this limit is going to be equal to 0 because the denominator is growing, the numerator is staying the same. That's going to make the fraction go to 0. And so since this is 0, that means that the top function is growing faster than the bottom function. So this polynomial grows faster than the natural log function. And the natural log function does grow really slowly here. You can see it kind of level off. It does something like this. Whereas the function x squared grows more rapidly than the natural log function. It looks something like that. Oh, and you can see a couple of graphs. We said in the first of these examples that e to the x grew faster. That's confirmed there. And then in the second one, we said that x squared grows faster than natural log of x. Let's see if it gives that. Yeah, there's some very good graphs. All right, so you can try, yourself to do this problem here. But if you just read one line later, it says e to the x grows more rapidly than x to the p than any polynomial or any power function. So actually that answers this question right here, that 2 to the x is going to grow faster than x to the 100. Because exponential functions, if they're increasing, they increase faster than power functions or polynomials. Okay. All right, very good. That will complete the section, and I have a class to get to. So we'll end the video here. And let's see if we can figure out how to stop this. All right. Make sure to leave a comment on the video or something to let me know that you enjoyed it. And I'll see you in the next one.